Okay, so thank you everyone for showing up. So I just want to say a few words about the past midterm. So I know that it's quite challenging as it's a remote exam, and some of you have encountered some technology problems like Excel or your computer, but I'm glad that we finally made it. And regarding the grades, I hope that we will have the distribution by next Monday. So hopefully I will be able to show you the overall distribution of the class next Monday. So you will see your relative standing. Yes, so regarding the midterm problems, it will be the topic for the discussion section this week. So if you're interested in knowing the answers, you can attend Thursday's discussion section. Since we don't have homework due this week, right? So the discussion section will cover the midterm. And then regarding the distribution of the letter grades, like what's the breakdown, what's the percentages, I can give you some rough numbers based on the last time I taught this class. So I would like to say that even though this class is quite technical, as you can see, because it's quite math heavy, which is quite different from some other classes you take in our department. However, I want to say that in terms of grades, I don't think I was harsh on that. So just to give you a rough idea, so the last time I taught it at the final, I still have 60 students in the class. So the class that used to be bigger. This time we have only 48 right now. So out of the 60 students, 14 students got at least A and A+. So that's about 23%. So to me, I think that's a quite good percentage among the whole class. So 14 get A and A+. If we include A-, then that number goes up to 22. So that's 36.7%. And if we count all the students who could get at least B-, so if I set a cutoff there, then we have 51 students. So that's how much? 85%. So 85% of students get at least B-. So then you can see how the distribution is roughly like. And I want to say that the distribution is not fixed. It's not saying that I'm going to curve your grades and give the letter grades just by sticking with those percentages. That's not the case. So what I will do is that I will look at your absolute grades, the numbers, and I will try to find the breakdown by looking for gaps. So for example, if two students have very similar grades, then they will be assigned the same letter grade. So that's how I generally do it. So but I understand that people may have different concerns or preferences regarding the grades. So therefore, I think it would be a good idea that you can see your midterm performance, right, relatively in this whole class, and then you can decide what's the best plan for you. Okay, so do you have any questions regarding the midterm? And the problems and answers will be given at the discussion section. And another thing I want to say is that if you see the problems, you can see that I try to avoid computation as much as possible. So I would say probably 5 problems need some number computations, but most of them are based on concept. So for example, the sum of independent Poisson is still a Poisson, and the sum of independent Gaussian is still a Gaussian, still a normal random variable. So we use those kind of things a lot. So I think the goal is that I hope everybody is familiar with the distribution of the mean of normal random variables and the sum of normal random variables. So those are the basic facts we are just going to use a lot in the following study in statistics. So for example, like for 100C, the class following this one, it will cover linear regression. So in that case, you are going to use the concepts we teach in this class, the MLE, the maximum likelihood estimator for the linear regression coefficient. So that will be the concept you're going to use in the following class. So that's why I would say the foundation taught in this class is essential for future study, especially if you're interested in getting a graduate degree in statistics. So do we have any further questions before we go back to our lectures? Okay, so if not, then I will start my lecture.
Oh, Professor.
Yes.
About the do you guys do you have like any extra credit homework or assignment for that? Like anything extra credit like that?
At least not for now, but I'll see. Yeah, so I think we used to, I think back in the old days, you know, this exam used to be taken by in person, right? In person, and also the problems used to be large problems. You have to write your derivations every step, etc. But this time we turned them into multiple choices. So I think that's just a format change. But regarding the extra credit, we may consider adding something in the final exam so that for students who have time, they can do that for the extra credits, but at least not for homework. I don't have plan for homework.
I see, thank you.
Yeah. Okay, so our midterm only covered materials up to the probability. So everything we have in the midterm is for probability. Sorry, I think I lost the, give me a second. I think my trackpad is not working. Okay, so everything we have talked about in the, or we have covered in the midterm was about probability distributions. So we talk about the moment generating functions, which is an important property of a distribution. Using that, we can derive whether two random variables follow the same distribution or what the distribution is for the sum of independent random variables, like the central limit theorem. Those kind of things were all based on the moment generating function. Use it as a tool for proofs. And then we talk about some distributions derived from normal random variables, including the chi-square distribution, F distribution, T distribution. Those are all commonly used distributions in statistics, but they are derived from normal distributions. So after we concluded that part, we started our discussion about statistics, which is how to estimate a parameter, the parameter of a distribution. So the first way we described is to use the method of moments. So here the idea is that we can write down the population moment of a distribution in terms of the parameters. And correspondingly, we can calculate the sample moments as the average of some kth power of x1 to xm. So then correspondingly, we will match sample moments with population moments by the order. So this is the first order sample moment, first order population moment. So we match them and then we solve a system of equations. So for example, if the distribution has two parameters, like if we have the mean and the variance as the only two parameters, and that's the case for normal distribution, then we just need to go to the second moment. Then we have two equations. Sample moment equals to first population moment, second sample moment equals to second population moment. And we solve the system of equations so that we can find the estimates of mu and sigma squared. So that's the whole idea of the method of moments. And if your parameter of interest is not equal to one population moment, instead it can be expressed as a function of population moments. Then the idea is to just replace the population moments by the corresponding sample moments using the same function. And then the result is called the method of moment estimator. So last week we talked about this approach. And second, we move on to another approach of finding an estimator. This is called the maximum likelihood estimation. So this approach find estimators in a different way. So to find the estimator by the name, we need likelihood. So likelihood is the most important concept in mathematical statistics. If I want to name one, you're going to see the term likelihood again and again in your future study. So what is it? The likelihood is defined as a function of parameter. All right, so here, this is how we define likelihood. It is a function of parameter theta. And what's the definition? The definition is that if let's say we now regard our IID, x1 to xn random variables as our data, okay? Our random sample, or this is our data. So given that if we assume our data each follows a continuous distribution, then the likelihood of theta is defined as the joint density of x1 to xn given this theta. Otherwise, if x1 to xn are assumed to be discrete random variables, for example, if your data n numbers are counts instead of some real numbers, if you model them each follows a Poisson distribution, for example, then the likelihood of theta is defined as the joint probability mass function of x1 to xn. Okay, so here the key is that when we talk about the joint density or joint mass function, the arguments are the n random variables. While we talk about the likelihood, the argument is the parameter theta. So even though the two sides have the same mathematical expression, they are two different functions because they have different arguments. So I hope this makes sense to people. And so to help you understand this further, let me try to just go back to my R and to do a numerical example, because I found that can be quite helpful for understanding the concept. Okay, so just give me a second. Okay, so now you should be able to see my desktop. And I'm going to give you a numerical example to help you understand what the likelihood is. So let's say that I draw data from a normal distribution. Okay, so let's say that I draw sample and IIDs from a normal distribution with mean mu, and I just set the variance to be 1 for simplicity. Okay, so let me say that in my data generation, I'm assuming that I know the truth. So I set mu equals to 1. Okay, I start from there. And then what I can do is that I will generate my x, which is x1 to xn data from mu. Okay, R norm. Let's say I set n equals to 100. So then I will sample n IID from this normal distribution. So mu is set to 1 and sigma stays as 1. So I don't need to change it. Mu set equal to mu. Sorry. Okay, so this is my data, right? So let's say if we do this generation, mean, sorry, my bad. It should be mean. If I do this data generation, then the x will look like 100 numbers from that normal distribution. Okay, then what's our likelihood? So here for each value of mu, we could actually evaluate the density of these 100 numbers given that mu. So now let's say that I have a set of mu list, okay? A list of mu values, the values I want to consider as my possible value for the mu, my guess for the parameter. So let's say that I don't know. So now we don't know the mu is equal to 1. So we will guess a range of numbers. So let's say that my guess is I consider numbers ranging from -1 to +2. I'm just making a random guess, or maybe a -2 to 2. And I will consider dense numbers. So I would say maybe by 0.01. So their gaps are 0.01. So then what I will do is that I will evaluate the density of each of these data at each mu. So that will give me the likelihood. Okay, so the likelihood list, okay, would be that is for each mu in the list, I'm going to evaluate the density of X at that mu. So to do that, I can use the supply function. I apply it to the mu list, okay, and I call each element as the candidate mu. Okay, and given this candidate mu, what I will do is that I will evaluate the density. Density function can be calculated by the d norm function. So then what I can do is that I can put my data in here, and then I evaluate density at the mean being this mu candidate, that possible value of mu. Okay, and so this d norm, if we check this help file, we can see that you can input a vector, right, of values to get the densities, but the output will give the density for each one. So let's say if I put d norm X at mean equals 0, for example. So you see, I'm going to get 100 density values, one per each xi. But what I need is the joint density. So here, because x1 to xn are IID, I can multiply their densities to obtain a joint density. And that's what I would do. So I would just do the product. Right? So in the product, you give it a vector, and then it will take the product of the elements. Okay. So then I'm going to get the likelihood for each candidate mu. And let's see what we get. Okay, so now I'm going to plot the likelihood values I get and their corresponding mu values. And let's see what we have. So let me also add a XLab. Maybe I'll just write this. Okay, so sorry, I think I should put it in the other way. What's wrong here? The likelihood, mu, sorry, I reversed these two things. So let me just change it. Y equals this, X equals this. Okay, then it should be fixed. Okay, this is the likelihood function. You can see that as I change the value of mu, the likelihood is taking different values. And where is this likelihood maximized? You can see it's close to the true value 1. So what MLE does, it is to find this position of mu value so that the likelihood is maximized. So if I do that, I can tell you. So R can tell me which mu give me the maximum likelihood. So if I do which max, it will give me the index of the mu value, 305. Then let's take a look at that mu list. I just grab the index that maximizes the likelihood. Okay, so you see our MLE is 1.04 and the true parameter value is 1. Okay, so this is what we have. And then now you can see that if I repeat this whole process by increasing my sample size, let's see what happened. Now increase the sample size. Now I can set the sample size to be very, very big. Say, let's say 10 to the 4th. Okay, so it's 100-fold more than the previous one. And let's see what happens to this MLE. So I'm going to regenerate my data. Okay, unfortunately, you don't see it's closer to it. And the reason is actually because, I can tell you the reason. The reason is because here for the mu list, I'm only taking this small gap. And also, this already tells you that here the MLE is just one realization of a random variable. So you can imagine that if I repeat the sampling for many, many times, I am going to get a distribution of the MLE. And then I can see how the distribution of MLE changes. So let's do that. This is for one realization. Now, let's say that we now repeat this for maybe 1,000 times, okay? So we will get 1,000 MLEs from 1,000 random samples. Let's do it. Okay, so sorry. So then for this, I'll do 1,000 times. So this is what my habit. So in R, we should try to use apply as much as possible and try to avoid doing for loop as much as possible because R is very poor at handling for loops. So for loops are very slow. Okay. So you see, I'm just copying the whole procedure here. And every time I'm going to get an MLE based on a random sample. Okay. So let's see that what we have. So this, I call this MLE list. Okay. So I should remove the plot, sorry, because otherwise you can see it's being plotted every time. So every time, oops, what this means is that given my data generated randomly, given each random sample, the likelihood function is changing. So you now see this effect. Right? Because the likelihood is the function of theta given the x1 to xn. But now every time when I do simulation, x1 to xn are changing. So therefore, based on x1 to xn, the likelihood function likelihood functions are changing. Does that make sense? Yeah. So now you see, I'm done. I'm done with running this code. And then let's see what the distribution of MLE is. Now for this one, I can plot the density of the 1,000 MLEs I obtained. You see, this is how it looks, or probably I'll just do histogram. Maybe that's better. If we do histogram, you see, the MLEs themselves follow a distribution and their mode is very close to the true value one. So seeing this result, then you can see that the reason we say an estimator is a random variable is simply because the estimator is a function of our data. And our data x1 to xn is a set of random variables. So therefore, you see, for one particular data set, the MLE may be here or maybe here. And they can be far away from the true mu. However, statistics is not talking about one particular realization, but the overall distribution. So this one, we can see that at least intuitively, you can see the MLE in this case is actually unbiased because if you have its all realizations and take the average is actually at 1.0. So I'm not sure if this makes sense to you at this time. So the intuition behind what we're doing under the MLE, maximum likelihood estimation. And also later, we're going to talk about the theory of MLE, which can already be seen here. That is, here, the MLE has a normal distribution, actually. So here the MLE have this normal shape. So the MLE theory will give us its mean and its variance. So therefore, you could have the theoretical distribution without doing the simulation I did. You can imagine that in the old days, say 50 years ago, without powerful computers, what I'm doing right now is not possible. So people have to use math at that time to really derive, what the distribution of MLE is. So that's why mathematical statistics was the foundation. Because at that time, without computers, what else can you do? How can you talk about the uncertainty in your data? You have to rely on probability theory, have to rely on math, and that's our foundation. But nowadays, thanks to the computer technology, I was able to do this numerically, so we can see this distribution visually, even we don't understand the math. Okay, does that make sense? Okay, so now what I want to say is that now if I include n to 10 to the 4th, and then we can see that the MLE distribution would be narrower. So we'll see that. So I'll just quickly do this again. So I'm going to do this for large sample size. MLE list 2, okay, for that large sample size, and I will remove this plot line so that can save us some time. Oops, my bad. I should stop it. Sorry, yeah, because it was using the old N. So I'm going to use this and it will take longer because now the sample size is larger. Hopefully not too long. Okay, sorry. I think I'll kill it without waiting for longer. Maybe I'll just decrease the sample size and let you see the effect. Okay, so previous we have 100. Now let's do 10. And let's get this list. This should be fast. Okay, now we're done. So now let's compare these two histograms. So this is the one we have for n equals 100. Okay, this is the distribution of MLE. You can remember the range is from 0.7 to 1.3. Now let's compare it with the second list when the sample size n is set to 10. All right, so now you see the range is wider, right? Here we have 0 to 2 instead of 0.7 to 1.3. So that gives you the intuition that distribution of MLE depends on the sample size. The larger the sample size, the smaller the variance. And this was actually one of your midterm problems, right? Regarding how the variance of sample mean would change with the sample size. So the intuition is that larger sample size will give us smaller variance for an estimator. And here the estimator is MLE. Okay. So I'm going to save this part and I'm going to post this to CCLE later so you can play with our code to help you understand. But at least I think what I want to say is that this plot, okay, this plot we have seen before is the likelihood function. So when you change the parameter value, the likelihood value changes correspondingly. And when we compute likelihood, we are fixing our data. We're fixing x1 to xn, so we can have this function. But when we change x1 to xn because they're random, then the shape of this function will change accordingly. Okay. Any questions before we get back to the notes? All right, so last time we give you 3 examples about how to derive the MLE. The first example is this Poisson parameter estimation. So we have x1 to xm from a Poisson with parameter theta. So for Poisson, the most important property is that its mean and variance are both theta. So this is something we should be very familiar with. Okay, and then what we do is when we write down the likelihood, we write it as the joint probability mass function of x1 to xn. Because of IID, it's the product of each xi's mass function. Then we have this formula, okay? And then we're going to maximize this function for finding the value of theta. Find the value of theta, then maximize this function. Because this function involves exponential product, we take its log because log preserves the monotonicity. So the maximizer of this likelihood is the same as the maximizer of the log likelihood. But with the log, then the form of the function is much simplified. So now you see we have a function like this. And then because this function is differentiable in terms of theta, we just take the first derivative, set it to 0, and check the second derivative being negative. So the calculus trick. And then we found that setting the first derivative to 0, we obtain this value. And we verify that the second derivative is always non-negative, non-positive. So therefore, we conclude that this value at which the first derivative is 0 is indeed a global maximizer, and we call that MLE. And here, in this case, the MLE, just by coincidence, is the same as the MOM, method of moment. The second example is a little bit more trickier because we are dealing with two parameters, mu and sigma squared for the normal distribution. Therefore, the likelihood has two arguments, the two parameters. And because here x1 to xn are continuous, we define the likelihood as their joint density. Okay, again, by IID, we factorize them as the joint density as the product of individual densities. We multiply the densities, this is what we get. Again, this is an exponential function. We can simplify it by taking the log. After we take the log, then you can see we have mu here, sigma here, right? So sigma here. So the function is simpler, and we want to maximize this function. Again, this function is differentiable in terms of both mu and sigma squared. So here we treat sigma squared, the parameter, as one term. So the parameter is sigma squared instead of sigma. When we take, then we take the partial derivatives and set both to 0. Okay, and solving this system of equations, we are able to get the result like here. So last time I said that if we want to be rigorous, we should check the second derivatives. Here it is a Hessian matrix, and check that it's negative definite. But since we are not assuming a high level of linear algebra here in this class at least, so that's why I skipped this step and just saying that, yeah, this is verifiable, that we can show that indeed it's negative definite, and then we can conclude that these two are the global maximizer of the likelihood function. So this is the MLE for mu, this is the MLE for sigma squared. Okay, so these are the two typical problems of doing MLE. The final problem is a little different. Here, the parameter is a boundary parameter. So it defines the domain of a uniform distribution. So in this case, the boundary is unknown, and we want to estimate it. So again, we define the likelihood as the joint density of x1 to xm. Here, their IID. We factorize the joint density into their product, into the product, their marginal densities. And then here's the density for HXI. So here, the special thing about this density is that unlike the Poisson or the normal distribution, the parameter is not in the boundary, right? In the Poisson case, all the random variables are non-negative integers. That's the restriction, but it's not depending on a parameter. For the normal distribution, the random variable xi can take any real values, not depending on the parameter. But here, the density of xi depends on the parameter theta. So if this xi is less or equal than theta, it can receive a positive density. Otherwise, zero density. What does it mean? It means that you can never draw a value larger than theta, because by definition, that's the uniform distribution. It's impossible to draw a value greater than theta. Okay, but because theta is involved in the domain, we need to mark it here. So basically, the density of xi given theta is taking 1 over theta only if xi is less or equal than theta. Otherwise, this indicator will give me 0, and the density is 0. So realizing this, when we take the product of the marginal densities of x1 to xm, here it is. We have n indicator functions. And we know that if one indicator takes value 0, then the whole term is 0. So therefore, it's non-zero only if all the indicators are non-zero. That means all the indicators conditions hold. So x1 less or equal than theta up to xn less or equal than theta. If one of them doesn't hold, then the indicator will be 0. Okay, and then you see everyone is under theta is equivalent to that. The maximum of x1 to xm is under theta. Okay, so we change the indicator to that. Okay, this is our likelihood function. But now our normal trick of doing the log transformation and differentiation is not working here. The reason is because you have this indicator function and it's 1 or 0, only takes 2 values, and we don't want to take log of it. One reason is that we cannot have log 0. People know that log 0 is negative infinity. So that's why we have to just optimize this function as is. But this function, because this indicator function is a step function, so theta, if it is below this maximum xi, indicator 0. Once theta reaches this maximum xi, indicator becomes 1. So that's why there is this sharp change at this maximum xi value. Before that, the likelihood stays at 0. After that, the likelihood reaches this 1 over theta to the power n, right? And then after that, as theta further increases, this function is a decreasing function of theta, so the likelihood decreases. So this is the shape of this likelihood. So if you can draw this shape of this function, then the optimizing problem is done. We don't have to do any differentiation anymore because it's very obvious that here this maximum xi maximizes the likelihood. And that's our answer. Okay, so for this one, it's not a traditional problem because log transformation differentiation no longer works. But regardless of that, we're still maximizing the likelihood. That's our ultimate goal. Okay, so do people understand this problem? I feel like probably this one is harder to understand than the previous two. All right, so if we're all good, so I spent quite some time to recap everything we have done. The reason is that this was before the midterm, so a while ago. All right, so now we are going to continue our discussion about the property of an estimator. So if you recall, so when we talk about the properties of an estimator theta, which estimates theta hat, which estimates theta. Okay, so when we talk about this property, the one we introduced is the bias. Okay, and the bias of this estimator is defined as the expectation of the estimator minus the true parameter. And this is also showing that the estimator is indeed a random variable. So that's why we talk about its expectation. Now the question I have for you is that a random variable have an expectation. What's the other thing we talk about it? Because for a random variable, besides expectation. Variance, yeah. So I saw Ran just saying variance while muting herself. Yeah, indeed. Yeah, variance is the second property. So we define the variance of theta hat. It's the variance, right? And this is based on the definition of variance. So basically, it's this. It's theta hat minus its own expectation. This is the definition of variance by definition. Okay, so variance is the degree, right? Like the spread of the random values around the expectation. The bias is whether the expectation is equal to the true parameter value. So then another thing you can see is what if I replace this expectation by the parameter value theta? What is it? That's the property we use the most. It's called the mean squared error. Mean squared error, short as MSE. Okay, so the MSE of theta hat is defined as the expectation of theta hat minus theta, right? The ultimate difference between the estimator and the true parameter value. And we are taking the square because we don't care about the sign, whether it's less than or greater than, that's different, but we don't care. We only care about the magnitude of the distance between theta hat and theta. So we take the square. So the sign of the distance is out. And then we would sign of the difference is out. And then we take the expectation, because we're not just interested in the particular realization of theta hat, how far away it is from theta. Instead, we're interested in the overall, on average, difference between theta hat and theta. So considering all the randomness in theta hat, how does it do in terms of estimating theta on average? Okay, so this is the mean squared error. So one important result is that we can actually express this mean square error in terms of bias and variance. Okay, so this is an important result everybody should pay attention to. And I would say this is the foundation of statistical learning. So I think for the another class, you may read the book called Introduction to Statistical Learning. In that book, you're going to learn a lot of techniques for doing data analysis. And in that book, this is a crucial result when we compare different methods. So MSE, it can be expressed as the square of the bias plus the variance. Okay. So this is a result that's crucial because you can see it's very simple and also it says a lot. So let's say that if we have two estimators, that is, let me say this. So if we have two estimators, theta hat 1 and theta hat 2. Okay. So what this implies is that if the MSE of theta hat 1 equals to the MSE of theta hat 2, okay, then we will have this result. If the bias of theta hat 1 is less than the bias of theta hat 2, we can conclude that the variance of theta hat 1 must be greater than the variance of theta hat 2. Okay, so in other words, if the two estimators have the same MSE, then the one that's doing better in bias is doing worse in variance. And this is what we call the bias variance trade-off. Okay. So I'm not going to touch the statistical learning part because I'm assuming you're going to learn that later, but you can just know this term here. So bias variance trade-off is a central theme when we compare statistical models and when we talk about different algorithms. So maybe I can give you a little preview. So basically, when we say a method or an algorithm has a large bias, we usually mean that the algorithm or the model doesn't fit your data very well. Okay, but when we say a model has a large variance, it usually means that when we fit the model to the data, the model fits data super well, but we worry that there may be overfitting. So therefore, when you apply this complicated model to new data, the fitted model will change drastically. So that's what we call the variance. But when you fit a simple model, even though it doesn't fit your data very well, but if you fit it to another data set, the fitted model may look similar. So they're not doing overfitting. So you can say that, okay, it has small variance, it's quite stable across data sets. However, there might be a bias. So it doesn't fit your data very well. So maybe you don't understand what I'm talking about right now, but this is something you're going to see later if you take more stats classes. But this is what we introduce in the context of estimators, the variance bias trade-off. Okay, so the MSE is an ultimate criterion for quantifying the performance of an estimator because it's actually about how well your estimator is concentrated around the true parameter. So how well does theta hat concentrate on theta, right? So if it concentrates more, then we can expect that the overall squared deviation is small. So the MSE is small. Okay, so now we're going to introduce, so we're pretty much done with this part about the properties. So basically in this class, we'll talk about bias, variance, mean square error as the 3 criteria for evaluating an estimator. So the next result is very important theoretical result. So it's called the Cramer-Rao inequality. And people sometimes also call that the theorem, Cramer-Rao theorem. So this one addresses a very important question. What's the minimum variance of unbiased theta hat? So this perspective is, we know the bias is not good, right? So we only consider unbiased estimators for a parameter. Then among these estimators, which one can have the smallest variance? This is the optimal estimator because if an estimator is unbiased, then the bias is 0. If the variance is minimized, then the MSE is minimized, right? So basically, what's the best unbiased estimator? Okay, and just for your information, Rao is still alive. So he's already a legend of statistics. I think he just had his 100th birthday, maybe last year or this year. So yeah, but this is his contribution to the field. And the Cramer-Rao inequality is very elegant. So I would just say that, let me just quickly state the result. Okay, so we just have this, let x1 to xm be IID following a PDF density function denoted by theta. So theta is the parameter that specifies the density function. And here I'm leaving out this argument as a dot to mean that this is the value where we put each random variable in. So it's just the argument of the function. Okay, so let theta hat be a function of g x1 to xn. G is a function, be an unbiased estimator. Unbiased estimator of theta. Okay, then the key assumptions is about the smoothness of the density function. Okay, so then under smoothness conditions of F. So for example, in the Poisson case and also the normal case, actually the smoothness condition is satisfied because you can roughly see that the mass function or density function, this is actually a generalization. It can also be a mass function, by the way. So the mass function or density function are differentiable, but in this uniform case, right? It's not actually. It's not really a nice function because here we see that this indicator function has a jump, so it's not really smooth. So I can say that maybe for this class, because we don't want to be too technical to talk about the smoothness conditions, you can think that the common distributions we have talked so far, like the normal distribution, exponential distribution, gamma distribution, Poisson distribution, those distributions all satisfy the smoothness condition. But later you are going to see some special distributions that are not so well, that not so good. So that's why, you know, when people do graduate level statistical research, they usually need to deal with those more complicated cases. But for this class, since it's introduction, so we just deal with those nice distributions, and we assume that the smoothness conditions is hold. Okay, so then with this, under the smoothness conditions of the density function, that's the only requirement. We can say that the variance of this unbiased estimator must be greater or equal than 1 over n times this term, I theta, which we didn't introduce, but we will do next. So this I theta is called the Fisher information. Okay. All right. So basically, the Cramer-Rao inequality gives a lower bound for the variance of an unbiased estimator, which says that you cannot do better than this, right? Your variance cannot be smaller than that. This is the best you could do. So give us some lower bound estimation for the variance of an unbiased estimator. And I think it's very interesting that this is not depending on any specific form of theta hat. It only says it's unbiased. And so basically for any unbiased estimators you may achieve, this is the variance, the best variance you can have. Okay. Oh, and one more thing. I think I forgot to say that, but I should. I think I should. So regarding this MLE problem, this uniform one, if you do this using the method of moment, okay, if you don't do MLE, you do method of moment, then actually the estimator of theta is actually different. If you do the first moment, then what's the first moment? What's the first population moment of this uniform 0 to theta? Can somebody tell me? What's the expectation of this uniform distribution 0 to theta? Actually, I don't think you need to do any integration. It's just be the middle, right? Because it's uniform, right? Uniform, you have the same density, then you take the mean, it's the middle. So it's theta over 2. Then you do the MLM, method of moments. You should set theta over 2 to the first sample moment, that's x n bar, okay? And then solving that, it will give you the method of moment estimator for theta as 2 times x n bar. So that estimator is different from this maximum of x1 to xn. So this is the case where the MOM doesn't equal MLE. So I just write here. So here the theta hat MOM is just 2 times this, which is different from what we have here. While the theta hat MLE is just the max of xi and I from 1 to n. Okay, so but I can say is that what I can say is that for both these, so for the MOM estimator, if you take its expectation, then clearly, right, it's unbiased. And for the MLE here, it's a little bit trickier actually. We need to deal with the distribution of the maximum of random variables, which is actually beyond the scope of this class. I'm not going to talk about here, but if you're interested in, this is a very important, useful fact in statistics about the distribution of the extreme order statistic. What's the distribution of the maximum? What's the distribution of minimum? But what I can say is that, so given its distribution, you can see the MLE is going, if you take its expectation, okay? So it's not exactly equal to theta. However, that bias will go down to 0 as n goes to infinity. So in that case, so maybe I can just say a little bit more. So if the bias is not 0 in terms of a finite n, but let's say if it's something with n in the denominator, so when you let n go to infinity and the bias goes down to 0, then we can call this estimator not unbiased, but adding an adverb asymptotically unbiased, which means that when n goes to infinity, it becomes unbiased. So speaking of that, maybe let me grab a new piece of paper. So for example, recall that what we did is that, so for this right sample variance, if we recall, this definition, we know is equal to the variance of each xi, right? It's equal to the sigma square. So it's unbiased. But what if we have this 1 over n thing? So what if we do n minus 1 divided by n, this thing? So this is the formula you would guess if you don't know statistics. You do dividing n instead of dividing n minus 1. Okay, so therefore we can clearly see that the expectation of this biased estimator, I can get a constant out. Okay, so I just put it back. This is the expectation. So from this, I can tell that the bias of this estimator is simply the expectation minus the true parameter. Okay, and then it's just okay. So clearly, this is biased, right? So we can conclude that is biased. But this bias, as I said, has this dividing n. So if we let n goes to infinity, it will go down to 0. So we can say that this estimator is biased, but asymptotically unbiased. Okay, so asymptotics is talking about the scenario when n goes to infinity. So although this is, again, a little beyond the scope of this class, but I just want to introduce this term. So because later you're going to see people, when they talk about mathematical statistics, you are going to see this again and again. What they mean? They mean the n is going to infinity, basically. So, and also in the midterm, right? So I sent a message. I said that if we don't say n is large, you cannot simply assume n is large. When we just say n, then it could be any n. Okay, so back to our thing. What is feature information? Feature information, so here we are defining it based on the likelihood of one observation. Okay, so it's defined as, maybe I'll just put it here. So it's defined as the based on the log likelihood of theta with one observation or one random variable as our data. So basically here, the log likelihood, I use the small l as theta. It's just defined as the log of the, I'm just using density as a representative, but it could be the mass function. Density or mass function of one random variable, I denoted by x at value theta. Okay, so F is the PDF or PMF of random variable x. Okay, and this PDF or PMF is specified by parameter theta. And we take the log, so it's the log likelihood. So therefore, when we change value of theta, the log likelihood value change accordingly. That's the thing we have seen, right, in the R simulation. Okay, then what's feature information? Feature information is defined, it's denoted by I. I stands for information. I of theta. It's the information of the parameter. It's defined as the expectation of the derivative of this log likelihood. Okay, so it's basically the expectation of the squared first derivative of the log likelihood. This is feature information. So then the question I have for you is, when we take expectation, there must be a random variable in the expression. What is the random variable? So Ran, would you like to unmute yourself?
Is it theta?
No, not theta. Theta is a fixed parameter. So here we have theta, here we have theta here. So theta can be 1, can be 2. Whenever we put theta here, we need to calculate expectation. But in the expectation, theta is not random. So it's actually x. The reason is because when we define the likelihood function, it is based on a particular value of x, right? But x itself is random. So that's why you saw that when I do the simulation, when I change my x1 to xn by randomly sampling from normal, then the likelihood function changes accordingly. So in other words, when the x changes, then the likelihood function changes. So therefore, for a different likelihood function, the derivative will also be different. But we are just evaluating the derivative at this fixed value theta. So for value theta, we fix it, we evaluate the derivative at that theta, we take the square of the derivative, but this derivative is going to change if x is changing. So that's why we're taking the expectation with respect to x. Okay, that's the key. So this is with respect to x, okay? While in this definition, theta is a constant, not a random variable. Even though it's a constant, we can still put in different constant values and see, for constant 1, what's I1? For constant 2, what's I2? We can still do that. But the expectation is with respect to the randomness in x. So that's why maybe it's clearer if I write it using the original form, and then that's what you will see in many books. So you can write it as d theta f, okay, and the expectation is for x. Okay, so what does it mean? Squared. It's the square of the first derivative. So basically, you're just going to know that, how fast is the likelihood changing at my current value theta? Okay, how fast is changing at my current value theta? And I don't care about the derivative being positive or negative, because we know the first derivative is the what? Is the slope, right? The slope could be positive, could be negative, but we don't care. We just take the square of it. And we take the expectation over all possible values of x. So maybe let's go back to the screen I was showing. All right, so looking at this figure here. So this is our, you can think about this as our theta, this is our L theta. Right, we're not taking the log, but that doesn't matter. So you can just imagine this is a log likelihood. Then at every theta value, we are going to get a gradient, a slope here. So that's the slope. We are going to take the square of it. So here you can see the slope is large, while here the slope is 0, right? But all the slopes we get here is based on one realization of x. As I change my x, the curve may be different. Okay, so at those different curves, I'm going to get the derivative again. So what I will do is that basically for every value theta here, I will get its derivatives across all the likelihood functions based on my different realizations of x. And then the average of that derivative would be my Fisher information. Okay, so that's the whole idea. Okay, so you can see that what this is meaning, right? What does this suggest? So intuitively, this is saying that, oops. Intuitively, this is saying that if I change my value of theta, then go back here. If I change my value of theta, then the likelihood function changes a lot. Okay, and this is true for all possible realizations of x. On average, then my likelihood function changes the most at this value theta. And what does it mean? It means that this theta is a sensitive spot of my likelihood function, right? By averaging x for sure. So it's a sensitive spot. And that means that I can easily differentiate this theta value from other theta values. Because when I change the theta value a little bit, then the likelihood function changes a lot. So therefore, I can easily detect it. Then the Fisher information is big. So basically, here the Fisher information, if you put theta as the true value, okay, the true value of your model, then if the Fisher information is big at that true value, it suggests that you can easily distinguish that true value from the nearby values. And then you can, your MLE, maximum likelihood estimation approach, would work well. Does that make sense? Okay, so maybe I think when we come back next time, I can show you some figures about the Fisher information, like how it changes with theta. So then you can see that, interestingly, so given the same model for different values of theta, then the Fisher information may be different. However, we expect that the Fisher information is the largest at the true value of theta, because that's our target. What we want to estimate. Okay, so before we give you that intuition next time, oh, actually it will be next Wednesday, because next Monday will be a holiday. Actually, I forgot to say that. So that's why I'm going to talk about the grade distribution next Wednesday. Okay, so another result is that the Fisher information can have an alternative definition. Alternative definition. It is the expectation, negative expectation of the second derivative. This is the alternative definition of the second derivative of the likelihood function, log likelihood function, with a negative sign. So what is the intuition behind the second derivative? We know it's about the curvature, right? Or the concavity. So basically a function like this. So let me just give you one example. If this is L theta versus another, log likelihood function, like, okay, in those two cases, for example, then we definitely know that the second derivative, so we can say that here, the negative, both second derivatives are negative for sure. But here, this one, in terms of this, okay, is bigger, is bigger on the right. Because the second one, the right one is sharper. And that's what we call the bigger curvature. And that's captured by the negative second derivative. So because in this case, in both cases, the second derivatives are negative. We know that. But the degree of negativity is greater on the right side because it's sharper. So that's why here the Fisher information can also be defined in this way. And this reflects the intuition I said. It's about how sharp the likelihood function changes around the value theta. And because this involves random observation X, so that's why we have to take expectation. Okay, so regarding why we have these two equal, it's the magic of the density function, which is how we define the log likelihood. It's the log density. Otherwise, I can say that for a general function, if it's not a log likelihood, this doesn't hold in general. We cannot say the second derivative has any relation with the first derivative. That's not true. However, because here the log likelihood function is defined as a log density function, we have this magical result. So we can show that the second definition, alternative definition, is just equal to the first definition. So to prove that, we are going to use the fact that the density integrates to 1. Okay, so we have this, since the density, if we integrate across all possible values of the random variable, this is equal to 1, right? By the definition of the density. Now we take derivative for both sides. So it's basically d theta 1, and that's 0, right? And now the smoothness of f will be crucial, which is the thing we need for the Cramer-Rao inequality. Okay, because of the smoothness condition of f. Okay, that's the key. That's the key. So because of the smoothness condition, we can swap the differentiation integration. We have d theta sorry, there's no bracket here, is equal to, we can swap it d theta. Okay, so that gives us the first step. Okay, now we need to go here. We need to, oh, sorry, I made a mistake here. It should be log, okay, because the likelihood is the log f. Okay, so now we are going to deal with this term. Okay, now we have d theta log f. Let's say that I still use the lowercase x to mean the argument. Now we apply the chain rule in calculus. Okay, so the chain rule will give me log thing first, right? So I will get f x theta in the denominator. In the numerator, it will be the differentiation inside the log. So that's d theta f. Okay, that's what we have. Okay, so therefore, what we can say is that with this relationship, then we can have a very interesting thing by moving the denominator to the left-hand side. So basically, we can say that the d theta, I put the right-hand side to the left-hand side, f theta is equal to this thing, d theta log fx theta. the left-hand side times the denominator. Okay. All right. Now, if I do integration, something magic happens. So if I do integration, add integration dx to both, or I should say not add, apply. Apply integration dx to both. Then for the left-hand side, I'm going to do d theta fx theta dx, right? And based on what I have for this line, this is equal to 0. For the right-hand side, I apply d theta log fx theta dx. Now don't forget that this is the density of x, right? So it's a function of x times density of x dx. By definition, this is just the expectation of d theta log f. Now I write big X theta. The reason is that here I'm emphasizing this is the random variable, but over here small x is just any value the random variable takes. Okay, so now this is my first conclusion. This expectation is equal to 0. Okay, and then we will start from here next time. So basically, I hope everybody, before our next lecture, which will be in 1 week, I hope everybody can really try to spend time to understand future information and also to understand that when we talk about expectation, what's the random variable? That's always the most complicated thing. Even at the PhD level, I can say that many people are still confused about when we talk about expectation randomness, which random variable are we really referring to? So I would strongly suggest that people try to understand feature information. There are many useful resources online, for example, Wikipedia, right? And also maybe some YouTube tutorials. They give you very short introduction, then give you a lot of intuition behind it. So we will come back to finish this proof to show that these two definitions of feature information are actually equivalent. But before that, I hope everybody can spend some time try to understand it. And we will assign a homework this time. Yeah, so basically the homework will cover things we did in the last week, not in the midterm, but we will do them in the final. Yeah. All right, so I will see you next Wednesday. Bye.